Thanks for having me, especially thanks to Thornton Tomasetti, Core Studio, and Constru, of course, and everyone associated with this conference. My name's Nate, and I am from Omaha, Nebraska. Does anyone know where that is? Not having a good year. Not having a good year with that. I'm the founder and CEO of what we kind of refer to ourselves as a digital design agency. And the way that we kind of position ourselves within the building industry is that we are operating in effect as consultants. This means that we are, engaging in various capacities with architects, engineers, contractors, and owners to help realize kind of what we believe as being a very important part of the future of the building industry, which is in data-driven methodologies and techniques. One of the things I always like to emphasize is that while technology sits at very much the core of what we do in terms of like establishing workflows, I think more foundational is just the idea of pursuing evidence-based thinking, agile methodologies, and ways for us to perform continuous self-improvement on the problems that we engage. We are working on a pretty wide variety of different projects, and as I mentioned, in different capacities. There's a selection of some of the projects we've been a part of in the last 3 years as a business. We're only 3 years old and we only have 4 people, so we're really, really small, which is much smaller than certainly WeWork. I was kind of looking at those stats, I'm like, oh boy. And one of the things that kind of runs as a thread through kind of our thinking on a lot of the issues that we see at conferences like this, and certainly is going to be present in the work that I hope comes across in the narrow thread that I'm going to try to weave here, is that it's very easy to get caught up in the potential of technology and the use of algorithms as ways of solving problems. If I were to critique the current state of how technology is often adopted, and certainly it's becoming more and more pronounced, is that oftentimes I think we are producing solutions in search of problems, when I think that there is many well-defined problems that need to be solved, and some of which are not easily solved by technology alone. And I think I really appreciated the conclusion of the last presentation that really kind of touches on people as being kind of a main driver for a lot of this stuff. We are experiencing as an industry skills shortages, skills gaps, the availability of processes and the adoption of processes and standards being other kind of core foundational parts of this. So I'm going to be focusing on a very kind of narrow section of the work that we do, and it is a set of research that I conducted very closely with my colleague, who is also in the audience, Dave Stasek. We recently put together a white paper on what I'm about to show you, and as it relates to uses of machine learning and the improvement of data quality and uses of machine learning to improve data quality in the context of building problems. So, it's always interesting to kind of go back and think about, what is machine learning? And, if you read the literature and the popular literature on the subject, everyone's going to come up with like different definitions. This is actually the best definition that we found. A computer program is said to learn from experience E with respect to some class of tasks T and performance measure P, and its performance at tasks in T is as measured by P improves with experience E. So basically, we have this algorithm. You're giving it a lot of information, and ideally the ability for this algorithm to perform improves with the amount of experience that you give to it. Kind of this idea of continuous improvement of the algorithm and continuous refinement, which you saw, of course, in a bit of in the last presentation. I don't think that especially at conferences like this, that we're any stranger, our industry is any stranger to sort of machine learning and these ideas, and we certainly see it in a lot of the work that's presented in places like this. We ran a workshop yesterday that was quite fun. We recently put out an open source tool called LunchBox ML that is tied in with a Lunchbox plugin for Grasshopper, and basically exposes a series of general purpose machine learning nodes that allow you to kind of engage in different problems and tie them into your algorithms. I think one of the more popular approaches that we've seen, of course, in using machine learning is kind of the improvement of fabrication processes. This is an example of a complex paneling system that is then using a Gaussian mixture algorithm to identify relationships between different traits and characteristics in panels, and then kind of perform groupings and clustering, ideally allowing the user to refine their design and produce parts that can be fabricated, of course. We're also kind of interested in this idea of, we've also started to see this applied, to things like point scans, reality capture, and the identification of features within built elements. This is an application of the exact same Gaussian mixture algorithm that was used to identify panel features and cluster things together, and in this case being used to, as applied to a point scan, that is then kind of identifying the individual brick components of a very kind of flat set of data, right? And then of course, I think all of us are familiar with this idea of using things like evolutionary algorithms and genetic algorithms to kind of find solutions, optimize for certain criteria, kind of more of a bottom-up manner. What we see less of, I think, is what we call supervised learning techniques, and this involves kind of the use of more data-hungry algorithms. It requires availability of structured data as the back end upon which the learning algorithm is able to improve itself given more data. We kind of see this present in the uses of like regression algorithms, wherein you're kind of supplying it, say, a list of points, and then you're using regression tools to kind of predict, say, curves. We did an interesting study yesterday with the group to say, like, okay, well, can we use a flat set of points and teach an algorithm as a sort of set of input data to predict the actual curve that exists on a sort of a curve scanned wall from which we can then start to build features from it. And of course, I think there's other sort of scenarios that one can envision for supervised learning techniques wherein you're feeding information about spatial characteristics. I think we saw a little of this in the last presentation as well, and in a sense using the predictive qualities of these algorithms to aid a designer in making decisions about a space. In this case, this is a study that we did where we took a series of office environments. We surveyed the kind of content, furniture, attributes of these spaces, and then started to use that as a labeled data set that would then allow the designer to say, okay, now I have a new set of spaces, what actually should go in them, and can we actually use kind of the machine to make predictions about what actually belongs in a space and support these workflows. However, there is a problem to all of this, I think, and one that is often overlooked in these types of studies, is that a lot of the ability for us to leverage this technology is often limited by the quality of data at our disposal, and even our ability to sort of capture and reliably access this data over time. So I bring this up. This is actually a snapshot of a report, a type of report that we've done for clients before, where we are kind of performing audits of a business, and people are curious to know about, okay, well, how do we actually situate ourselves relative to the marketplace? How are we doing in the adoption of standards, et cetera? This is a snapshot of a report that was of building information models for a major retailer that has, they have like 4,000 stores across North America, and the question became, they're interested in, can we actually use our building information models as a way for us to benchmark and use them as assets to help us predict future space needs, not so unlike what you saw in the last presentation, right? But when you actually drill down into these digital assets, you find really fun and interesting things, such as the idea that only 45% of the Revit families present follow any kind of real naming structure. You see in the labeling of spaces inconsistent naming even on simple objects like closets. How many ways are there to label a closet in a medical facility? We could probably find the answer to that and show you how big the problem actually is, right? So there's this kind of fundamental sort of in kind of the mode of production that we are often operating in, sort of this level of data quality that needs to be addressed. And that's kind of where this research has led us, is that we're not kind of positioning machine learning in this particular research context as like a way for us to support the generation of, say, new design or predict future need on facilities. It's actually to help clean things up. We're kind of using machine learning as a bit of a janitor in a way to help us as an industry realize kind of the, establish a foundational data set that can help us then implement these technologies and improve the basis for what we work. So this methodology involves a couple of approaches that kind of string together. If we look at this diagram again, just very briefly, we have sort of a harvesting stage. How do we collect the data, and can we capture it consistently into data structures that are readily available and readily accessible by others? Can we mine this data, i.e. then start to perform queries on it and construct data sets that can then be used as training devices for machine learning algorithms, which then can kind of go back into other data sets and apply what it has learned in order to improve other assets. So at the core of sort of the harvesting approach that we're looking at is a technology that we've started to implement with a couple of clients in a couple of different capacities. We're calling it Minecart. And essentially what it is, it's about taking what is effectively a file-based approach to models. We still operate in a file-based world, I think. And a project may be made up of many, many models representing the same building. And it's very hard, I think, for an organization to get a clear picture of the data in its totality that it may have. And so this first part of kind of the exploration is then how can we start to aggregate this information into a single source of truth in a way, or a single kind of resource. Luckily, while I would say data is quite inconsistent among the BIM files that we have at our disposal, the structures with which this data is stored is quite robust and quite mature. These are a couple of diagrams taken from kind of the ancient express schema that is actually sitting at the foundation of IFC files and step files in the sense that it's able to describe entity relationship structures and kind of allow us to kind of take reliably information at different scales of a model and start to put it together and piece it together. So we're kind of exploiting this idea that, okay, well, data may not be consistent. We do have consistent structures, and therefore it might be easier for us to start to harvest and take advantage of it. So this has led us to the design of a kind of a database schema that allows us to aggregate this information, harvest data from models, and capture it in a consistent relational format, and also accommodate high volumes of information. Right, a building is not a low volume information asset. It actually requires us to, if we're aggregating this stuff together, to really think about relational structures, relational integrity, and things of that nature in order to kind of actually get these attributes to align with themselves. And along the way, of course, we're building harvesting tools that are, very straightforward user interfaces that just allow us to select, say, a variety of IFC files or a set of Revit files and then push them to this database. So it's kind of this efficient way of capturing information into a consistent structure that can be analyzed together. And the advantages of which then we have this ability to then mine from this database and kind of get snapshots of a portfolio, as was mentioned before, run queries that allow us to establish and pull out attributes. This is really the core of a lot of what we're doing. SQL database, SQL script, tables. Really mature stuff. I mean, this stuff has been around since the 70s. I mean, there's nothing kind of groundbreaking about SQL. But the way with which it can actually be applied, I think, is kind of interesting here. But the part where this starts to make sense to us is then being able to get front ends that help us interpret and create cross sections of this data to gain some form of insight. This is an example of like a model quality dashboard that we've put together to help us support evaluations of firms' digital assets. We're looking at the way with which various standards are applied, the model in comparison to various best practices that exist in the kind of the building information modeling workflow. And of course, the same exact data structure, we've also built front ends that are a little bit more about insight into portfolios of work and allow us to start to compare different attributes of a portfolio, say it's building program, or it's sort of content makeup across a project, in the aim of helping kind of owners or people that are interested in helping kind of to guide a portfolio make informed decisions about where improvement can be made, right? And then this is a fun thing we did. We made this, I think, as part of our one of our summer research interns made this, actually tapped into the database and made a custom IFC model viewer that taps into our database, generates spatial geometry, and just allows you to start to query this from a third-party custom model visualizer. A couple of weeks worth of work, and an intern can go a long way, I think, in helping us kind of pursue different ideas like this. This kind of then brings us to learning. So the idea that we are establishing a robust way of capturing data, we are trying to establish structures that allow us to then create essentially training data sets. This is not the most exciting use of machine learning. I'm sure you have seen or will see in conferences like this. But I think it's an interesting one because it starts to address a core problem. Again, data quality. Can we improve our ability to apply quality data points and thus improve our ability to analyze the buildings that we make and gain insight into them? So this workflow is describing a supervised learning method. The crux of this method is in capturing good data or data that we know is reliable. If we look at, for example, a cross-section of a healthcare firm's models, they might have done 500 projects in the last 10 years if you're working for if you're kind of collaborating with a very big healthcare company, right? Maybe only 10 of them have really rigorously applied modeling standards. And so in some cases, what we're doing here is saying, okay, let's find the best stuff. Let's kind of understand models that actually do have well-applied, rigorous data standards, well-labeled data, consistent naming of spaces, and things of that nature. And let's use that as like a learning data set from which we can then push in poorly labeled or even unclassified spaces, and then have basically the machine learning algorithm work on relabeling those spaces such that you're then having better quality. So this feedback loop is you have an unclassified or poorly classified or inconsistently applied set of standards on. We're passing them through a supervised learning workflow. It's using known data with known attributes and well-applied data to then basically refactor and reassign these spaces to known standards. This is a proof of concept, so the algorithm that we actually ended up producing and the results are actually quite dumb. So just a preface before we kind of evaluate how smart this thing actually was. But I have a point to make about that as part of future work, of course. One of the ways that we kind of executed on this scenario was we did use Lunchbox ML, which is our kind of, again, open source machine learning toolkit that we've put out there as part of Rhino Grasshopper. It allows us to do forms of supervised learning. This is kind of a diagram of how this technology kind of situates itself within a Grasshopper definition. We're revisiting one of the first plugins I ever wrote, which is Slingshot. Slingshot lets you connect Grasshopper into relational database management systems and pull data down. So we're actually connecting into the BIM database, pulling it into the algorithm. We're then formatting the information that we're getting and gathering as training data, and then we're testing it against unlabeled volumes and then thus producing some results. Other components to this, and this is where kind of the design of algorithms becomes interesting, is that in addition to using data collection methods, we can also start to weave in algorithms that allow us to interpret the information about a model, its geometric attributes, things like adjacencies, sizing of spaces, and start to run analysis on these things to kind of further enhance the effectiveness of the learning behavior. And the end goal is to kind of create these taxonomies of of how a space can actually be classified and described, and based on those descriptors apply a robust or kind of standardized classification to those spaces. So what you're seeing here is an example of the training data that's produced by bringing things through from the SQL database into Grasshopper. You know, we're kind of looking at the aspect ratio of spaces. We're looking at the level that a space exists on. Is it small? Is it a regular space? What are its neighbors around the space? And finally, based on, we're using an industry standard classification system called an OmniClass to then kind of insert a classification piece that can be used globally across many projects. And so this is kind of the product, in a way, of then executing this on an unlabeled volume. We are using a naive Bayes machine learning algorithm class, which is a probabilistic classifier. And so what you kind of see here is actually the effectiveness of what we've done. So based on like a data set that had like maybe 3 well-labeled buildings, healthcare facilities in particular, we then passed an unlabeled healthcare facility into it, and we can kind of see is the level of learning that and certainty that this algorithm is able to produce. So these are spaces in the blue that are high probability of being a certain type of space and therefore would be assigned a certain value. These are medium probability spaces where it's, maybe about 50% sure that this is actually a space that has been identified correctly and thus would have a classifier assigned to it. These are low probability spaces where the algorithm is just like, I don't know, it could be this with 20% chance that it's correct. And then this is like an absolutely like, we have no idea. I have no idea what the space is that you sent into it. Which of course kind of starts to get to, kind of, I would argue, a further component to this work, and it goes back to that initial definition of machine learning, is how do we improve upon this? Well, we have to keep making and expanding the data set, right? We need to keep including options and new ways of analysis. We need to continue to push buildings into that training database, which of course continues to improve the accuracy and the likelihood that correct spaces are assigned to other data sets. So that kind of leads us to then future work on this space. This is some of the things that we're thinking about in terms of how we can continue to expand the way with which this kind of algorithm successfully classifies spaces and can kind of inject these standards into existing models and thus improve data quality. We're no strangers over the years to having built like basic various spatial syntax and analysis models. Even going back to my early days as a designer at MPBJ, this is something we're very interested in, is like kind of understanding, okay, how can we actually analyze space, analyze kind of adjacencies, analyze view corridors, and all these kind of become interesting attributes for us to then push into these algorithms and improve its effectiveness. And ultimately what I see occurring then is that over time, it really does come down to people, and it comes down to architects in order for us to really kind of realize the potential of data-driven practices and processes. It does require kind of the onus is on people to really start to apply standards, up our game when it comes to really understanding data quality and produce ways with which we can understand space in a more quantifiable way to support these types of activities. So that's it for me. I'll kind of leave it at that, and I look forward to the panel discussion here.